Good morning, ladies and gentlemen. May I have your attention, please? Thank you. Please raise your hand if you didn't get a red mark for today, the 16th. Is everybody good? All right, let's go ahead and practice translating given system of linear inequalities, right, whose feasible region, that is the collection of all solution points, is already shown in the highlighted region. Okay, so what we can do is consider each boundary equation separately and then decide whether or not, all right, to include a greater than, a less than, a greater than or equal to, or less than or equal to, depending upon the solid versus dashed nature of the boundary line, as well as its relationship visually compared with the feasible region. So I'm first going to go ahead and do our special red line. If it had been an equation, right, a boundary line, the equation of a boundary line, it would be x equals the x coordinate of every single point on the red boundary line would be 5, right? So x equals 5 would be if it were an equation. The green boundary line looks to have a y-intercept of positive 5, right? And a rate of change, a slope value of down 1, 2, 3, 4, and over 1, 2. So it looks like down 2, 1, down 2, 1. So it looks like a slope of negative 2. So if the green boundary line had had an equation, it would be y equals 5 minus 2x for start value 5, and then plus bx plus rate of change x. Looks like we're going down 2 for every 1 unit we scoot over. Awesome. And then lastly, if the blue boundary line had been an equation, it looks to have a y-intercept of negative 4 and then up over 2, so up 2/3 is my slope. So y equals, and this time I could do mx plus b if I wanted to, 2/3 x minus 4. Nope, 3/2, isn't it? 3/2, up 3 over 2. So 3/2 x minus 4. Go ahead and raise your hand if you had the red boundary line correctly picked out, the red one, x equals, and then the y 5 minus 2x, and then y equals 3/2 x minus 4. Okay, but these weren't equations at all. In fact, these were inequalities, and so we're going to go ahead and with a big swath erase those equal signs and now decide based on the orientation of the boundary line and the feasible region whether this should be greater than or less than and so on and so forth. So we'll take a look at the red boundary equation. Given that the line is dashed, is this going to be a greater than or a less than or a greater than or equal to or less than or equal to? Well, it looks to me like my feasible region is to the left of x equals 5. Therefore, we want a less than or equal to. But because my boundary line was dashed, I'm going to get this strictly. So go ahead and raise your hand if you had x less than 5 now for your final red boundary line inequality. Good job, you guys. Let's take a look at the green. For the green, is my feasible region in relation to the green above or below it? Mark?
For which one?
For the green one.
Above.
Above, thank you. Is the boundary line of the green boundary line solid or dashed? Joe? Dashed. So put it all together. What symbol will we have for my green inequality? What symbol will we have? Blake?
That's the greater than.
Greater than. Awesome. Raise your hand if you have y greater than for the green boundary line. Y greater than. Good job, you guys. Number 1 to go. Green boundary line, or sorry, blue boundary line. Everybody find it. Is my feasible region in relation to the blue boundary line above it or below it? Above it or below it? Caitlin?
Below it.
Below it. Good. Is the blue boundary line solid or dashed when graphed? Jacques?
It is solid.
Solid. Put it all together. What symbol will I have here? Go ahead and tell the class. Hannah? Less than or equal to. Raise your hand if you have y less than or equal to for your blue boundary. Way to go, you guys. So here we'll go ahead and do one finishing touch. Yes, that's right. Voila. And we now have a system of linear inequalities whose solution set, whose feasible region is shown as the highlighted region. Nice job, you guys. All right, let's go ahead and pick a solution point and see if it satisfies that linear system of inequalities algebraically. What solution point did you test? Carson?
4,
4, 0. Let's go ahead and test 4, 0. Visually, I see that Carson's test point is in my feasible region. Therefore, it should satisfy these algebraically. Let's go ahead and check. Ready? Is 4 the x-coordinate less than 5? Yes, 4 is less than 5. Well, I feel good about that. Is 0 greater than 5 minus 8? Well, 5 minus 8 is negative 3. Is 0 greater than negative 3? Yes, it is. And lastly, is 0 less than or equal to 3 halves times 4, which would be 6 minus 4 is 2. Is 0 less than or equal to 2? Yes, 0 is less than or equal to 2. And so that solution, or that test point, I should say, 4 comma 0, satisfies each of those 3 inequalities in the system. Therefore, it must be a solution to the system, along with, well, an infinite number of other points that are also in that region. And so when we have a feasible region here in this shaded region, we've got an infinite number of points that satisfy all 3 of those inequalities. I also would pick 4, 0 because it looked like it would be an easy one to test. Awesome work. What questions do you guys have about today's Bellwork? So let's go ahead and switch gears and let's take out your assignment number 6. I'm going to pause the recording while we check it before resuming after we've handed it in. Ladies and gentlemen, today we're going to continue working with our systems of linear inequalities and yet use them just as one piece in an overarching strategy known as linear programming. This is a capstone strategy that's going to put together a lot of the foundational skills we've been developing, like writing, right, and translating written description into a linear equation or linear inequality, solving a system of equations to, by finding a point of intersection, right, or solving a system. Using now our substitution as we just did in our Bellwork to check if a given point is or is not a solution. All these individual skills are going to now be put together in this overarching strategy called linear programming. We're going to use it to find optimal solutions to real life problems. So this is a super cool application of mathematics, and I really look forward to these next 3 days. Today will be kind of an introduction to linear programming. Then we have spring break, and when we come back, we'll jump wholeheartedly into it. We'll take a look at how we can use it to solve some bigger problems. We're going to have a video game manufacturing problem. We're also going to have an astronaut space trip and determining bars and nutrition drinks that you're going to take in. And so we've got some good things to look forward to. All right, let's go ahead and take a look at this problem together. We're going to develop a strategy for handling a linear programming problem, and then you're going to have a chance to work with your partner and earn a stamp today on a bobblehead problem. But first, let's take a look at our Red Hots and Juice Box problem. Aaron may have earned a C in math, but he deserves an A for business savvy. Yes, that's right. Aaron ran an illegal junk food store at his high school. He sold Red Hots and juice boxes out of his backpack for 50 cents a piece. Every day before school, he stopped at a store and spent up to $10 on his contraband goodies. He paid 20 cents per bag of Red Hots and 40 cents per box of juice. However, he could only smuggle a total of 40 items in his bag. So Aaron's challenge was to determine what combination of Red Hots and juice boxes would yield a maximum profit, making sure he remembered Big Bruno's order, who demanded 4 Red Hots and 4 juices every day, or else. I want to fill in the blank with what that or else is. It might be another BSI, borderline school appropriate. Luckily, he remembered how to use linear programming from his advanced algebra class. Oh yeah, so here we've got the setup, right? Aaron is taking his $10, and he can use any portion up to $10 each day to buy Red Hots and juice boxes at the store. Then he comes to the commons, right, and out of his backpack he sells these for trying to make a profit. Our job is to figure out the combination of Red Hots and juices that she should buy each day and sell in order to maximize his profit. We're going to use this as an example, a template for our linear programming strategy, and then you guys are going to practice it later today on a bobblehead problem. All right, so the first thing we want to do is define our variables. In fact, step 1 for a linear programming problem is identify and define your variables. So let's go ahead and look at the problem. At the end of the day, what will we have determined? And that can be a guide for choosing what x equals or what y equals or what a equals or what b equals, whatever we're using for our variables. So let's see. We want to determine what combination of Red Hots and juices would yield a maximum profit. And so we're going to go ahead and let X be the number of red hots that we should purchase. So let's let X equal the number of red hots. And let's let Y equal then the number of juice boxes. That's just not going to do. So let X equal the number of red hots and then Y be the number of juices. Okay. The next thing we'll do in step 2 is to translate our given information into a system of linear inequalities. Each constraint, right, each constraint in our problem is going to translate into a separate linear inequality. And then we'll put those together kind of like we did in our Bellwork when we go to make a graph of the situation. So let's go ahead and translate the maximum number of items in his backpack into a constraint. So let's go ahead and stand back in the problem. Remember Aaron, his backpack is only so big, right? He can only fit so many items in it, and so that's a constraint in our real world problem. How many items can he fit in his backpack, right? How many items can he fit in his backpack? Ian?
40.
40, good. So I don't know how many red hot boxes X I'm going to purchase, or Aaron's going to purchase. We don't know how many juices he's going to purchase, but he knows he can fit at most 40 items. So a linear inequality that would represent that constraint would be number of juice boxes, X, plus number of red hots, X, plus number of juices, Y, is at most, that's less than or equal to 40. He could bring 10 items, he could bring 15 items, he could bring 40 items, but he can't bring any more than that. So at most would translate into less than or equal to. So there's my backpack constraint. X plus Y is less than or equal to 40. Everybody good? Let's take a look at our next constraint, the minimum number of red hots. Recall that Big Bruno, right, demands 4 boxes of red hots every day and 4 juice boxes every day or else. So we could translate that into a constraint. The minimum number of red hots would be X is greater than or equal to 4, right? He needs at least 4, and at least would translate into greater than or equal to. He needs at least 4 red hots for Bruno. Similarly, he needs at least 4 juices because Bruno requires 4 every day or else. You don't know what that means, all caps. And lastly, we'll translate the maximum items for $10. And so in here we need to take into account the cost of our items because Aaron has $10 to spend each day, right, at the convenience store on his way to school. So here we go. $10 is the most he can spend. And for every box X of red hots he purchases, right, how much of that $10 does he spend? So how much does each box of red hots cost? Cody?
20 cents.
20 cents, so it costs 20 cents for each bag of red hots. So for every X bag of red hots, it costs him 20 cents. So we'll go ahead and do 0.20x when combined with the amount he spends on juices. And so how much does each juice box cost? How much does each juice box cost? Samantha?
40 cents.
40 cents, so 0.40y. So 20 cents for every red hot bag and 40 cents for every juice box. That has to be at most again, so less than or equal to. Is that right? Less than or equal to $10 because he can't spend more than he has. He can't spend more than $10. Awesome. So we've taken our given information, our constraints, and translated those into linear inequalities. The next step in a linear programming problem is to go ahead and write the objective equation. Our objective equation is our goal, right? Our goal. Our goal is not to put as many items into our backpack as possible, right? Our goal is not to spend all of our $10. Our goal is to maximize profit. And so whatever quantity it is that we're trying to optimize, sometimes it's minimize weight or minimize gas used, right? In this case, it's maximize profit. That's the equation that I'm going to write. If I want to maximize profit, P, I'm going to write a profit equation. P equals So let's write our objective equation. We want to maximize profit. So I want to maximize profit. I'm going to write that down just so I know what I'm trying to do. I want to maximize profit. And so I want a profit P equals equation. And now I need to take into account the profit that Aaron makes for each sale. Well, we know that he sells Red Hots and juice boxes for 50 cents a piece. He sells them for 50 cents a piece, right? Does that mean he makes a profit of 50 cents for every Red Hot box that he sells? No, because it costs him 20 cents. So what's the profit for every Red Hot box that he sells? What's the profit? Hannah? What's that? 30 cents? I'm down. So I'm thinking his profit would be given by 0.30x plus juice boxes cost 40 cents and he sells them for 50 cents, so 10. So 0.10y, that looks like my profit equation. Everybody see that? You see how you get the 0.3 and the 0.1? You took away cost, right? We took away, sorry, his sale price minus his cost to him equals the profit that he gets to keep. All right, now let's go ahead and graph each of the constraints. We're not graphing the objective equation. This equation never gets graphed at all. We'll use that later to figure out the optimal solution. What we're going to do is graph the system of inequalities, the constraints, just like we had for Bellwork. And so we're only sketching the system of inequalities. So let's go ahead and graph those on our xy coordinate plane. So what do we need? We need x plus y is less than or equal to 40. So we need x plus y is less than or equal to 40. We need x is greater than or equal to 4. We need our juice box constraint, y is greater than or equal to 4. And we needed our cost constraint, that was the 0.2x plus 0.4y equals 10. Sorry, less than or equal to 10. All right, let's do it. Let's graph that system of inequalities on the same xy coordinate plane. But first, we need to go ahead and determine a scale. So it looks to me like my original graphs, if x were to equal 0 and plotting that first equation, x plus y is less than or equal to 40, my boundary line equation would be x-intercept of 40 comma 0 and y-intercept of 0 comma 40. So it looks like we need to get at least to 40 on my scale. So let's go ahead and count out our stuff. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So if we went by 4s, then we'd have 0 to 40. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. If we went by 4s, then we'd get all the way to 40 on both my axes. So let's go ahead and try that. I'm going to label my horizontal axis. My horizontal axis is going to be my x-axis. That is the number of, what was x again? What did we pick x to be? Red Hots. So let's let that be number of Red Hots. Red Hot bags that he purchases. And let's let our y-axis be the number of juices, right, that he purchases. And we need our scale. It looks like we're going to go by 4s, we decided. So 4, 8, 12, 16, 24, 28, 32, 36, 40, 4, 8, 9, 12, 16, 28. And we're going by 4s. 4, 8, 12, 16, 20, 22. Uh-oh. 24. 28, 32, 36. All right, so I purposely chose to label different values on my scale just so I can get a sense of where they are. You could label every tick mark if you wanted to, that's certainly fine. In the interest of time, I just labeled select values. Now let's go ahead and sketch a graph of my black constraint, x plus y is less than or equal to 40. We can do this using x or y intercepts if we so choose. If I graph the black constraint, I know when x equals 0, y equals 40, so I have the y-intercept 0, comma 40. I know when y equals 0, x equals 40, so I have the x-intercept 40, comma 0. Let's go ahead and make that black graph now. So 0, comma 40, and 40, comma 0. I'll connect those with the black line here. And there's my back constraint. Everybody see it? All right. Now let's go ahead and graph our red hot constraint. For Big Bruno, we need at least 4 red hots. So that's going to be a vertical line that connects every single coordinate, right? Every single point his x coordinate is 4. So that would be a vertical line. And that would be at x equals 4. There's my red hot constraint. And I'm going to make this a red line. Y greater than or equal to 4 is the number of juices. I'll make that a green line. And we want to be connecting all the points that share the same y coordinate, and his y coordinate is 4, so that'll be down here. And we want that to be a green line. Very nice. And lastly, we need that blue equation. So we could graph that a couple different ways, right? We could solve that for y and rewrite in slope-intercept form to sketch a graph, or we could do x and y intercepts. Which would you, because it's in standard form, which would you rather do? Like to solve it for y, or like to do x and y intercepts? IDK or IDC? Big difference. Rachel? Solve for y? Okay, we'll solve for y. In order to solve for y, we subtract over the x term. 0.4y equals negative 0.2x. Again, I'm just doing the equation of my boundary line to make a picture. And plus 10. Dividing each term by 4 gives me y equals negative 0.2 divided by 0.4 is negative 1/2 x. Plus 10 divided by 0.4 would be 100 divided by 4 would be 25. Is that right? So let's do 10 divided by 0.4. 25. Hooray! So for our blue constraint, we want a y-intercept of 25, a y-intercept of 25, and a slope of negative 1/2, right? Negative 1/2. So here we go. 25 would be right about here. On my scale, a slope of negative 1/2 would be down 4 over 8. Down 4 over 8. So I'm going to go down 4 over 8. I'm going to go down 4 over 8. I'm going to go down 4 over 8. All right, let's see if we can make a graph here. And I wanted this to be my cost in blue. Huh? How you feeling today? All right. Now is the moment of truth. We need to take into account that each of these boundary lines, in fact, came from a inequalities. So we need to consider the overlap of my half-plane solutions and determine the feasible region, where all those shaded regions would overlap. So here we go. Everybody look. The black line. The black boundary line. If it had been solved for y, we'd get a y less than or equal to, y less than or equal to. So we want above or below the black boundary line. Right? Above or below the black boundary line. Taylor? Below. Good. We want below that. The red hot line, x greater than 4, we want to the right or to the left? Jacob?
To the right.
To the right for x greater than. Good. The y greater than or equal to 4 green juice box line, we want above or below that? Samantha? Above, because it's y greater than. Good. And then lastly, the y, the cost one, we solved that for y. And this was positive, so we would not change the direction. So we want y less than or equal to. Is y less than or equal to above or below? Andrew?
Below.
Below. Let's put it all together and we'll shade our feasible region. So here we go. I'm going to grab a highlighter. That'll be pretty sweet. Yeah. Yeah. That's a fun little color, isn't it? Hey. Pretty good. Pretty good. All right. Not that it's going to bother me for the rest of the day. Awesome. So now we've got our feasible region, right? We've got our feasible region, and we've completed step 4. We're going to graph each of the constraints, and we're going to clearly label the feasible region. So we can go ahead and call this the feasible region. Or with my second borderline school inappropriate joke of the day, FR, right? There's our FR right there. FR, feasible region. Suspect. Hey, suspect, Mr. Fritz, I'm watching you. Find the coordinates of each critical point. The critical points are the vertices of that feasible region. So if we look at our polygon of the feasible region, the critical points are the corners of that feasible region, right? It makes sense that if we're trying to find the optimal solution, that is maximize profit, it makes sense that we're going to look at the extremes, at the edges, along the edges of that polygon feasible region in order to determine the maximum profit that we can attain. So let's go back and get those critical points. We'll go ahead and take a look. Some of these we can get for free. For example, the intersection of the x equals 4 red line and y equals 4 red line, that's going to be 4, 4, and we can get that without any work. The intersection of the black line and the green line, we'll be able to get that without too much trouble. I'll take the green y value, y equals 4, and I'll plug it into my block equation for y. When I do that, I get x plus 4 equals 40. Therefore, x is 36. And so 36, comma 4 is another critical point. Let's go ahead and write those down so far. So I've got 4, 4. We've got 4, 4. And we've got 36, 4. Feeling pretty good, okay. Let's see, are there any other ones that are easy? Well, when x equals 4, this red line, when it hits the blue equation, we can determine the value of this point by taking x equals 4 and plugging it into the blue equation right there. So let's do that. So when x equals 4, I get 0.2 times 4 is 0.8 plus 0.4y equals 10. 10 minus 0.8 is 9.2. And 9.2 divided by 0.4 is, survey says, Andrew?
And which one, sorry?
Oh, sorry. 10 minus 0.8 is 9.2, and then divide by 0.4.
Divide by 0.4.
On your calculator.
Yeah,
23. So it looks to me like when x equals 4, y equals 23 on the blue line, so we can add that to our test points. So 4, 23. Let's add that. So I'm feeling pretty good. We've gotten 1, 2, 3 of our corners, but we're missing 1. Everybody, let's go ahead and find that last corner of my feasible region. It looks like it's right here, right? It's right here. Now that's close to a lattice point, and it might be, but I can check and see for sure if I get this, solve the system of equations with blue line and black line. We see where the blue line and black line intersect? That would be solving the system black equation and blue equation. So that's what I'm going to do to go ahead and determine that point. So I'm going to go ahead and solve the blue equation and the black equation. The blue equation and the black equation would be x plus y equals 40. So I'll go ahead and use substitution to do that. And plug in y equals negative 1/2 x plus 25 right here for y and solve. So x plus negative 1/2 x plus 25 equals 40, which means that 1/2 x plus 25 equals 40, which means that 1/2 x equals 40 minus 25 is 15. Which means x equals 30. If x equals 30, then y must equal 10. Is that right? 10? Going back into here, 30 plus 10 equals 40. So y equals 10. Which means this intersection point is 30, 10. I could also check that by going into my blue equation and make sure it satisfies the blue equation. So I'm going to check that. 0.2 times 30 plus 0.4 times 10 equal question mark 10. We found the solution to the system, and we found our final critical point. Let's go ahead and add that to our list. So we've got 30, 10 completes our critical points. So each corner of my feasible region is a critical point. Why is it called a critical point? Because these are the points I'm going to test, and one of them should be the optimal solution to the real-world problem. So let's go ahead and test each of these into the objective equation. Recall the objective equation was my profit. My profit equation was the P equals, and my profit was 0.3x plus 0.1y. So I'm going to test each of these into my profit equation. Here we go. I think it's time for the emulator. Can't make it anymore. All right. So I'm going to go ahead and test my profit equation. I want 0.3 times 4 plus 0.1 times 4 looks like 1.6. What's that? That's the profit that Aaron would experience if he just brought Big Bruno's order of 4 and 4, he'd get $1.60. So it looks like $1.60 is Aaron's profit if he did the 4-4 combination. Let's hope that it's more for 0.3 times 36. Oh my goodness. 0.3. I don't want any of that business. What's that? 0.3 times 36 plus 0.1 times 4. Getting better. 11.2 means that Aaron made $11.20. Yes? Great. 0.3 times, everybody test now. 0.3 times 4 plus 0.1 times 23. 3.5 is only 350. That's not so much. I mean, if you're a baller, 350 is not that much. I'm thinking the 1120 is kind of money. And let's check the last one. 0.3 times 30 plus 0.1 times 10. Survey says $10. That's better. As a result of testing each critical point, we now are equipped with enough information to answer the question that was asked. Conclusion, right? We want to state our decision now. How many Red Hots and juices should Aaron bring to school each day? Well, it looks to me if his goal is to maximize profit, then we want to bring the combination that produced the biggest profit. That was $11.20. It looks like Aaron should bring 36 what? What was the first coordinate? Red Hots and 4 juices if his sole goal is to maximize profit. That's how he would do it. So we need to answer the question that was asked. So Aaron should bring 36 bags of Red Hots and 4 juice boxes. Each day to maximize profit. That's pretty sweet. All right. As a follow-up, right, we've completed our main task. As a follow-up, how would our answer change if Aaron charged $1 for juices and 50 cents for Red Hots? So if we change $1 for juices and 50 cents for Red Hots, how would that change our answer? Well, the good news is we don't have to change our feasible region at all. In other words, his backpack is only going to hold, right? His backpack's only going to hold 40 items still. He still only has $10 to bring, and the cost of the Red Hots at the convenience store hasn't changed. What's changed is that objective equation, right? The one that wasn't graphed at all. And so the objective equation would be different now because he'd be selling for a different amount, which means his profit will change. So let's go ahead and do a quick check. My new profit for every Red Hot X now would be $1. Nope. Red Hots was still 50 cents, so nothing different there. That's still 0.3. But by charging $1 for juices, right, and their cost was 40, now isn't he getting 60 cents for every juice now? 60 cents? So let's see which is the best combination now. Again, we can do this by doing a simple check. With our grapher, we can do 0.3 times 4 plus 0.6 times 4. 0.3 times 36 plus 0.6 times 4. 0.3 times 4 plus 0.6 times 23. 0.3 times 30 plus 0.6 times 10. It looks to me like we've got 360. $13.20, and then whoa, $15 and $15. Whoops, not 15. So if you were to change his juice box sale price to $1 instead of the 50 cents, it looks to me like he's got two possible winners. He's got 423 and 3010, right? 423 and 3010. Which of these combinations then would be better? Well, if you were Aaron, which would you rather bring? If they both make the same profit, would you rather bring 4 Red Hots and 23 juices, or 30 Red Hots and 10 juices?
Some variety in there for the last one.
The last one, 30-10 variety. We don't want to run out with Big Bruno and then only be able to sell juices. On the same hand, 4 plus 23 is only 27 total items, so I might have a little bit more room, right, in my backpack for my advanced algebra text if I only bring 27 items. Versus, I bet my Red Hot bags are a lot lighter than 10 juice boxes. So maybe if I get the same profit, I want to bring the 30-10, right? Because then I only have 10 juice boxes, and those would definitely be heavier than my bag's Red Hot. So this would be a lighter backpack for the same profit. So you could weigh the scenarios, pick what you want. That's pretty awesome. What questions do you have about our first foray into a linear programming problem? Let's go ahead and sum up our steps then. So for our steps, we're going to refer back to our Aaron Red Hot problem. First, we want to identify the blank. That was what we did in step 1. Go ahead and decide with your partner what to put there. Then we're going to write the blanks as a system of blanks. Yeah, write it down with your partner, and then be ready to share. I'm going to go ahead and pause the recording, and I'll resume it when we share our final answers. You can talk about this. Okay, so our steps for a linear programming problem were just modeled with our Aaron Red Hot / Juicebox example. Let's go ahead and fill in our blanks now. And so, in step 1, we want to identify the blanks. Taylor?
Variables.
The variables, right? We let X equal the number of Red Hots. We let Y equal the number of juice boxes, right? I saw lots of people choosing constraints. Well, soon enough, we'll identify the constraints when we write the constraints, right? When we write the constraints as a system of inequalities. But our first step is to identify the variables. That's let X equal, let Y equal. So step 1 is identify the variables. Thank you, Taylor. Then we're going to write the blanks as a system of blanks. And so for step 2, we're going to write the blanks as a system of blanks. Aaron?
The constraints as a system of inequalities.
Good, thank you. So we're going to write the constraints as a system of inequalities. That's when we had the backpack constraint, X plus Y is less than or equal to 40 items. We had the Bruno constraint for minimum number of Red Hot bags and juice boxes. And we had the cost constraint. You only had $10 to spend. Write in blank for the quantity to be optimized. What? Write in blank, what could that be? Blake? An objective, right? An objective equation or an objective function. So that's our objective, right? What we're trying to do, our quantity to be optimized, that's our goal, our objective. Good. So write an objective equation, also called an objective function, for the quantity to be optimized. Nice job. Step 3, graph and shade the blank and include the coordinates of the blanks. What? Graph and shade the blank and include the coordinates of the blanks. What do you guys think for that one? Joe?
I said to graph and shade the constraints. I don't know what to put the second line.
And include the coordinates of the blanks. Okay. So after we wrote our constraints, we graphed, right, that system of inequalities, and we labeled the effort. We labeled that effort. FR. Borland School. Feasible region. Thank you, Joe. Everybody, feasible region. Graph and shade the feasible region. Uh-oh. I got a line for each of those. So we're fine. Feasible region. And include the coordinates of the, so what are the corners of a polygon referred to, right? What are the corners of a polygon called, Emily?
The vertices.
The vertices, nice job. The vertices. Thank you, good. 4. Blank each vertex in the objective function. So we're going to blank each vertex in the objective function. Casey?
Test.
Test, good job. We're going to test each of our critical points, our vertices, in the objective function. So that we can finally, Taylor?
State your decision.
Absolutely. We want to state our decision after surveying the different options in accordance with the objective. What was our original goal? We can now state our decision about the best choice for the situation. Make sure you have these steps correctly, because now with your partner, you're going to go ahead and apply them to the bobblehead problem. Yes, that's right. So we've got our steps and we printed these out for you. We're now going to work on the bobblehead problem, and at the end, stamp number 8. After you've checked with the posted answer key on the side whiteboard, just to the left of Joe and Andrew, or on the back whiteboard behind Ian and Rachel, you can see my posted work for the bobblehead problem. Make sure you're using those answer keys appropriately. You want to be checking them as you go along and not just copying answers. You're going to go ahead and check, and when you finally get the number 8 correct, you'll come up to the front desk and I'll give you guys a stamp at number 8. And then you can begin working on your assignment number 7. That includes a few book problems. I would do those first so you don't have to bring your book home over spring break. And then the worksheet is the second part of your assignment number 7. What questions do you have about what the rest of the class will look like? Awesome. Then I'm going to go ahead and stop the recording and upload it to our Moodle site.
Or